Okay, seems to be working. All right, other questions?
What about the modulus for linear low density polyethylene?
So linear low, that's in the notes somewhere. And so if we look at, I don't know it off the top of my head, but it will trend with the density. So we have a plot in notes, let me direct you to, is it notes 4? Or notes 5? Yeah, so in, let's see, notes 4, slide 10, we have this plot of density versus yield strength. And so that spans low density polyethylene, linear low density polyethylene, and high density polyethylene. So the density on the bottom here is from 0.91 all the way to 0.96. And so if we can control, how do we control the density of LLDPE?
Percentage of the monomer.
That's right. If you add just a few short chain branches, the crystallinity is high or low? High. If you add a lot of short chain branches, the crystallinity tends to be low. And so as we change the crystallinity, we change the density. And so we can move up and down this curve by adjusting the comonomer content. So comonomer contents tend to be between 1 and 7%. So we can get a big span in crystallinity with linear low density. And so if we go back to slide 7 in note set 4, linear low density has a density of about 0.92 grams per centimeter cubed. And so that puts us generally on the lower part of this near 10 megapascals or something like that. So there's, and if you look on slide number 4, or sorry, slide number 7, it says there's something called medium density polyethylene, which is just taking away more alpha olefin content. So you can, the linear low density polyethylene is really versatile because you can move the density around depending on the comonomer content. That's why it's used a lot now. Is that cool, Chris?
Thanks.
Yep. Chris, right?
Yep.
Yeah, okay, good. I'm getting there on the names. All right. Other questions? Kathleen?
For free radical, how do you decide like that one site is better for propagating than another?
Sure. So what's the key for radical formation? What radicals form? And so let me just draw it out. So there's two places where a styrene radical can form. We could form the radical here. One bond goes there and then we make another bond here. Or we can form the radical here. Which site do we form the radical on? We form it on this one, right? What type of carbon is this? Benzylic. So it's secondary as well, right? Because it's bonded to another carbon, but we call it benzylic. So benzylic radical. What's this radical? What type of radical is this? Primary radical, right? And so it turns out that this radical is resonance stabilized by this benzene ring, and so this is more likely to form. So the chain end, this lives the longest, which means that's the species that propagates. Primary radicals can form, but they form and then they disappear right away. So they're not very stable, and so it's very unlikely to have the chain grow like this. And so what we observe is that, say if we have an initiator or some radical species, right? This radical is one electron. We steal another electron from this double bond, and then we form the propagating chain end like this. And so when we run into another styrene, generally this radical will attack here to form a double bond, and then we'll get a radical, the growing chain end here. So this goes for PMMA as well. It goes for lots of different right? And so if we form the radical here, this one is now tertiary radical, right? So it's bonded to 1, 2, 3 carbons, so this thing is stable. It's also helped by the electron withdrawing character of this carbonyl right here. And so this is the most likely species to form. It's not going to form here. And so it's pretty simple in these sorts of monomers because this is very unlikely in most cases. So most things will propagate this way. So you'll attack another methacrylate. Etc. So this is why we often draw chains, say polystyrene, where the styrene or the aromatic groups alternate every other carbon. We often don't get styrene groups on adjacent carbons because we don't get radicals propagating like this. Where if we made this bond right here, we would have a primary radical right here, and that's no good. So we have 2 styrenes close together, that's not good, that's a weak point in the chain, and we would form this primary radical, that's not favorable either. And so this orientation is very unlikely, not very reactive. We flip this around and the chain will propagate. Is that cool, Kathleen?
Yeah, so then why doesn't propylene free radical?
Sure. So if we have propylene, right? We have an initiator here. We're going to form this, we're going to form this, and we're going to form our reactive species right here. So this is a secondary radical, right? So it has some moderate stability. It's better than a primary. But what can happen is that this can revert, and so you can form this double bond again, and then you can actually form the radical, where is it? So the radical can be down here, so it's 1 carbon away from a double bond, and this is called allylic. And this radical is very stable because it can resonate now with this, so you can form the double bond here, then form the radical right here. Or you can go backwards and you can form this double bond, then you can form the radical back here. So allylic radicals are stabilized by resonance, and they're long-lived and not reactive. And so it's a little confusing because benzylic radicals in styrene propagate no problem, right? But it turns out that allylic radicals are even more resonance stabilized than benzylic radicals. And so that's why these allylic radicals or polypropylene can't be made using free radical methods because of this resonance. So you can draw, this resonance structure right here, or you can go back and forth. And so because this radical is delocalized in 2 places, it's not going to react. So that's just a special case that you should probably know. But most other things with double bonds, unless you can form allylic radicals, will polymerize. So one thing that won't polymerize is vinyl alcohol. Because this is an acidic proton and it interferes with radicals. So that's something else to remember. When you see things with alcohols on them or see things with acidic protons, that's probably not a good thing for your free radical polymerization. Just something to remember. Water is bad for free radical polymerization because water will scavenge radicals. You good with that, Kathleen? Yeah? Zach?
Kind of along the same chain, I'm kind of confused at disproportionation and why it's important.
Sure. So disproportionation is what part of the polymerization mechanism?
The termination of the radical.
Yeah. What's the other termination mechanism for free radicals that we know of? Combination, right? So first of all, let's do the easy one. What's combination?
Use radical to turn that radical.
Two radicals. So two growing chain ends just combine, right? And you form a bond between these two chains. That's easy, okay? So that's combination. Disproportionation, we have a, let's write it out. So we have a radical species. Let's do it with polyethylene because that's easy. And then we have another chain end. So this is a radical, right? This is just a chain sitting there minding its own business. So what's the end result of a disproportionation or termination by disproportionation? What do we get?
Bring a hydrogen from somewhere and just finish the chain end.
You're going to grab, so this radical wants something, right? And what it's going to want is it's going to want one of these protons. And so what happens is you take an electron from that hydrogen, and so you'll get CH3. Right? So if this steals a hydrogen electron here, completes this bond, you get a CH3 here, plus what's going to happen over here?
Form a double bond.
You're going to form a double bond, right? So you're going to form a terminal double bond. So you're going to take, is that right?
Where's one from H?
What's that?
The methyl.
Oh, sorry. No, it has to be CH2, right? Because the double bond is right here.
So where's the other hydrogen?
Well, where does the hydrogen go?
So I think, oh yeah, that's a good point. Where does the other hydrogen go? Let me look in my notes.
That's what I was kind of, I think it's like that. I know there's a specific note set for disproportionation.
Yeah, let me make sure that I get it right here so I don't mislead you.
I think it's just two chains with free radicals, and one can just break a free radical from another and form a double bond.
Are they both free radicals for disproportionation? Let me make sure. That's right, so they both have free radicals. Let me look. So this is on page Propagation. This is on page 27 of the course manual. So we started it off wrong. So combination is just two radicals formed to form a growing chain. So what does the molecular weight do? If we have M1 and M2 right here, what's the molecular weight of this chain now? M1 plus M2, right? So if we have combination, I, and then because we're combining chains, right? And so who said disproportionation was two radicals coming together? Yep. So you're right. And so this is going to be what happens with disproportionation. And so we get something with unsaturated. So this is going to steal a proton from here. So that's plus, and then this is going to make unsaturated, right? Because we're going to form a radical here that's going to go there. This is going to come in there. And so we have CH2, CH, CH2, CH2. So we form unsaturated. And you notice that the molecular weight here, M1, M2, doesn't change very much, right? So you get the same molecular weight of whatever the growing chains were, but you have unsaturation now. So that's combination, disproportionation. You're right, they both involve growing radical ends. So why is unsaturation important in polyolefins? Why do we want to make unsaturated polyolefins? Go ahead, Zach.
Are they more stable, so easier to clean, like more separate?
Are double bonds more stable than single bonds? No, because we can react stuff on double bonds, right? And so what might we want to react on double bonds and polyolefins? What's the glass transition temperature of polyethylene? It's rubbery, right? And so that goes for lots of polyolefins. So if we make polybutadiene, polybutadiene is really liquidy, really soft, gooey material. Polybutadiene has a lot of double bonds in it. What can we do to polybutadiene to really increase its mechanical integrity? Cross-link it, that's right. And so unsaturation in polyolefins is really important because we can cross-link these unsaturated groups. So what's the best way, or what's the most common way to cross-link unsaturated polyolefins? Does anyone watch Star Trek here? Famous planet. Where Spock's from? We can vulcanize these double bonds. And what do we vulcanize with? Sulfur, that's right. And so sulfur can form the cross-links to make cross-linked synthetic rubber. And that's a really important process. So when we add dienes or when we get unsaturation, we can always cross-link these polyolefins with sulfur. That's called vulcanization. And that's what artificial rubber is in lots of cases. You good with that? Yep. Go ahead, Sonny.
Between what temperatures does crystals form, like this transition temperature?
Yeah, so that's a good question. So what are the major thermal transitions in polymers that we know about? Glass transition,
Melting.
and melting. So we have T, G, TM, TC, TM0, right? Those are the major thermal transitions. And so we can crystallize a polymer between TG and TM0. Okay, so that's good. What if we warm the polymer up to above TM0? What happens up here? What state is the polymer in? It's in the melt state, right? The melt is also called a liquid. And so there's no order, or it's amorphous. No crystals, right? Because we're above. No crystals because we're above TM0. So we crystallize in here, right? So crystallization temperature is called TC, where we crystallize. And so we know, let's put TC below TM. TM is always higher than TC, right? It takes some time to melt the crystals, and so that's why the melting temperature of polymers is higher than the crystallization temperature. That's different than small molecules, right? What's the relationship between TM and TC for small molecules? They're exactly the same, right? There's only one melting point and freezing point for water, or benzene, or ethanol, and they're exactly the same. Polymers are special because TC does not equal TM. So if we crystallize a polymer and we're holding the temperature between TM0 and TG, what two states do we have in the polymer between TG and TM0? We have melt, and the melt turns into what? Crystals. Great. Does the glass turn into crystals? No. So we have glass down here. Then we have maybe crystals. If we form the crystals here and then cool it down. And so remember, in the glassy state, the chains can't move past one another. There's no translational diffusion, and if those chains are stuck, that means they can't crystallize. And so we can form polymer crystals anywhere between TG and TM0. Yes?
Can you difference what is TM and TM0? What is the difference?
So what is TM0 all about? That's the melting point of the polymer when what is true?
100%.
That's right. So this is TM when the crystalline phase is 1.0. Does that ever happen in the real world? No, that's right. And so TM0 is just a theoretical point. So if the whole polymer was 100% crystalline, that would be the melting point. And so TM0 is actually where delta HF0 is as well. Right? The heat of fusion of 100% crystalline polymer is delta HF0, and we need to look up these two numbers, or we need to extrapolate from experimental data. One more question before I answer your question, Esther. So, can we crystallize above TM0? No, the polymer is just going to sit there, right? And we can't crystallize below TG because the polymer is stuck. And so all crystallization is going to happen in here. And so TC and TM move together. What determines TC and TM? Or how can I change TC and TM for different polymers? Or say I have the same polymer, right? Say I have polyethylene. How do I change what the crystallization temperature is? Zach?
Well, I guess you could anneal it to change it, so because as you add heat, the crystals get thicker, but you can also change your TM. because the TM is going to get higher as the crystal gets thicker.
That's right, crystal gets thicker also means we're converting amorphous polymer to crystalline polymer, so the percent crystallinity has a lot to do with what the TM and TC are, right? This is 100% crystalline up here. If TC is very close to glass transition temperature, I'm not going to form very many crystals because the polymer is starting to move slowly. And so the melting point of the crystals is going to have something to do with the percent crystallinity. And so if you wait and allow the polymer to crystallize more, you get a little bit higher TM. If you just form really small crystals, you have lower TM. Esther, go ahead.
So when polymer crystallize, do we say it's cooling from TM0 or T?
When a polymer crystallizes, well, you cool it to whatever the TC is, right? Because the TC is the crystallization temperature. So when you go from melt to crystal, that's a crystallization temperature, or TC. When you take a crystal and you melt it, that's a TM. So when you go from crystal to melt.
Oh, so I mean when we melt, it's TM, not TM.
That's right. So you never actually hit TM0, right? Because you never have 100% crystalline polymer. Yeah. So melt.
Because in order to crystallize, we have to melt it first.
What's that?
Yeah, I mean so in order to crystallize, we have to melt it. That's what I mean.
So in order to melt something, you need to have a crystalline phase first, right?
Oh, right.
Yeah. So you form crystals first, then you melt them.
Oh,
So when we go from melt to crystal, that's a TC. When we go from crystal to melt, that's a TM. So you always need to make some crystals at a TC first, and then you get a TM, right? If you don't have any crystals, there is no TM because there's nothing to melt. Yes?
In class, we were getting a little spread out on what our delta H was, like during the exercise, calculating it.
Uh-huh.
Are we supposed to find it as value joules per gram? Like if we were asked on a test, what are we trying to write down?
That's right. So I asked you two different questions. I asked you what the delta H is in joules per gram. So there's the heat of fusion in joules per gram, and that's my fault. And then the DSC signal is usually in joules, right? And so you're going to have to take into account, need to know the mass to normalize this. And so yeah, there was some confusion on the in-class exercise. So joules per gram is something that we can compare to delta HF0. So that's good, right? So we can determine the percent crystallinity just by simple relationship where the fractional crystallinity is delta HF over delta HF0. And so in the DSC signal, when we integrate that, we get joules, and then we need to know the mass of the polymer. And so if this is 10 joules and we have 100 milligrams in there, we'd have 100 joules per gram. Then we can compare it to the delta HF0. And so I'll try and be very clear on the exam if I ask you a question like this, whether I'm looking for just joules or joules per gram.
Thanks.
Does that make sense?
So how to calculate joule per gram?
Joule per gram, you need to know the mass. And so if in the DSC, you're going to get out a signal that says joules, right?
What if I get 10 joules?
So if you get 10 joules, you need to know how many milligrams of polymer, how many grams of polymer you put in the instrument to begin
Is it
with.
given? Is it given? Is mass given?
Mass may be given if you need it, but you need to remember if you do this experiment in your lab, you need to remember to weigh the sample before you put it in there. Yeah. So the software will often ask you, what is the mass of the sample? And then you type it in, and it will compute joules per gram for you. but you need to know how much polymer is in there. And we need to know how much polymer is in there because the mass of the crystal is directly related to how much heat is needed to melt the crystal. Because there's this linear relationship between how much material is there and how much heat is going to be required to melt that crystal, and so that's why we need to know the mass of that crystal so we can get this mass normalization.
If we get the joules from the DSC and we know the mass, we just simply divide to get delta HF.
That's right.
And delta HF0 will be given?
Delta HF0 will be given, or you'll have data to figure it out somehow through extrapolation.
Okay.
So remember, delta HF0 only occurs at 100% crystallinity. That's the key point. Yes?
So in the 8th question, in homework number 4, it says, it's given, suppose the rate of termination is high for given polymerization relative to moderate rate of propagation. Would you expect a high or low molecular weight? So do you mean by this question looking at the curves of molecular weight, like in step growth or chain growth?
Well, so okay, so let's talk about the different kinetic processes to make these polymers. And so what's the first step if we're going to do some sort of polymerization? So when we start off a polymerization, we've got monomer. What else do we need to make a polymer? Some initiator, right? And so the first step is we're going to do initiation, where we have some sort of initiator is going to react with the monomer. And so we can give that a rate, right? So rate of initiation. Okay, so this is the first step, and so let's make it easy and let's talk about chain growth polymerizations, right? And so we have some sort of rate of initiation, and so this will determine the initial slope for how fast we build up the molecular weight. Then we've got propagation, where we have a growing chain end reacting with the monomer. Right? And so this is the chain growing. How fast do you add monomers to the end of the chain? And then we have termination. And termination refers to basically stopping growing chains. So it's really the propagation step, the rate at which the growing chains add monomer, that builds your molecular weight, right? And then the propagation is going to work against that. The propagation is going to stop the growing chain end. And so if we have lots of termination and just moderate propagation, what's going to happen to the molecular weight? It's going to be relatively low, right? And so if we're getting lots of termination, this tends to give low Mn. If we have very good propagation kinetics, so if we have good propagation and low termination, we'll tend to get high Mn. And so this gives you some idea for designing polymerizations, how fast things are going to propagate, what's the termination step look like, and so you can start to tune the molecular weight by tuning the propagation and termination rates. Does that make sense? Yes?
Yeah, and for the 12th question in the homework number 4, so it's given that polyethylene sample was quenched quickly from the melt state. So that means that the crystallinity got increased by quenching in the melt state.
Okay, so that's a good question. So we start in the melt state. What does the polymer look like in the melt? All liquid, amorphous, no crystals, right? Quenching means what? Cool it down to what temperature? Below its glass transition temperature usually. So we'll quench it in liquid nitrogen or quench it somehow. And so if we go from melt to below TG very quickly, how much time do the crystals have to form? Zero or not much. So is the crystallinity going to be high or low if we give it a very short time to crystallize?
Low.
Low, that's right. And so in general, we'll get amorphous polymers from some sort of quenching process. And so what if we let the polymer sit there for a while? So what if we let it sit for an hour between TG and TM0? What happens? Crystallinity builds as a function of time. So that's in your notes if you look at, let's see, is it 10? No, it's 9. So if you look at notes 9 on slide 15, you see this crystallization as a function of crystallization time, right? So if you let the polymer sit between TG and TM0, the crystallinity will increase as a function of time because you're giving the chains more time to crystallize. And so if you quench a polymer, if you don't give it much time to crystallize, it's going to be amorphous. And so you'll get X-ray patterns and DSC patterns that tend to be indicative of an amorphous polymer without any crystals in it.
Would quenching increase the orientation?
Okay, so does quenching increase the orientation? No. What do we need for orientation to happen in a polymer? Flow, that's right. So quenching is not flowing. So quenching is just going from above, TM0 to below glass transition temperature, so you keep amorphous order. You always need flow for orientation. So does a quenched polymer have birefringence?
No.
Not necessarily. If it's still amorphous order, or if it's not sheared, or if there's no orientation, it's not going to have any birefringence. But a sheared polymer, even in the melt state, if you shear something, if you shear a polymer melt, you can see birefringence because you have those chains oriented preferentially. What's shear? So shear is a type of flow. Do you know shear like shearing? Let's see. Let's see. So a shear is a type of flow. So if you have a pipe and you have flow in this direction, shear force is the velocity is different at different points from the wall. That's called shear when you have a gradient in velocity. Go ahead, Lei.
So for question number 9 on homework 3, well, I still didn't understand the relationship between Young's modulus and the drawing speed.
Ah, okay. So the key in that problem is that higher shear gives higher orientation under most cases. So there can be some special cases where there's melt fracture and other weird stuff going on, but high shear, if you shear something very rapidly or shear something at a high rate, you'll tend to get more orientation. And so if we elongate a sample at 2 meters per second versus if we elongate a sample at 5 meters per second versus if we elongate a sample at 10 meters per second, this is the high shear condition, or high draw. Draw refers to pulling something, so you draw that sample out. And so when you draw that sample, you stretch the chains out, and so we have high orientation here. Here we have a little bit less orientation, and here we'd have even less orientation in this sample. And so the high shear or high draw gives high orientation. So you can think of two extremes. If you just have a vat of polymer sitting here on the desk, is it being sheared? No. Is it going to be oriented? No, it's just sitting there, right? Versus if I take that polymer and I start to pour it, and it starts to elongate, then we start to get shear, then we start to get some draw, so we get orientation in that flow of the polymer. So where we have high flow, let's say high shear, high flow, high draw, that all gives us high orientation, which gives us high birefringence.
And the Young's modulus is also increasing with that.
That's right. So why does the Young's modulus increase? Say I'm going to measure the modulus in this direction. Why does the modulus increase for the highly oriented sample? Go ahead, Zach.
Since all the chains are going in the same direction, you've got the covalent bonds all acting in the same direction, so you're going to have a higher modulus with the chains.
That's right. If I pull on this thing, I'm basically pulling on all the covalent bonds in the backbone, and those are very strong bonds, right? Versus what type of bonds are between the chains? Van der Waals forces, right? And so it's very weak in this direction, or weaker, but it's very strong in the orientation direction. And so that's why we orient polymers when we process them. That's why we orient fibers. That's why we draw fibers. That's why we biaxially orient plastic bags, because we want strong tensile properties in both directions. And so the shear and the orientation goes with the birefringence and also goes with the modulus as well. You good with that, Lay? Yeah. Other questions? Yes?
For metallocene, you have the two different kinds of kind of the shears, and then you had them from chain. You wanted to know which one gave isotactic and which one gave
Syndiotactic.
If they're superimposable, that gives you I just don't understand why that is.
Okay, so syndiotactic is what type of stereochemistry at each carbon? What does it mean? Alternating stereochemistry. And so one has right-handed stereochemistry, one has left-handed stereochemistry. So they're mirror images of one another. And so when you look at this example right here, when polypropylene, or when propylene monomers, let's say it's going to approach like this, I think that's how I drew it in the homework. Here we have mirror symmetry, and so the way these catalysts work is that monomer is going to approach here, coordinate, and then that frees up a spot on this side, so the monomer will approach here, and they'll approach from alternate sides to to add to the growing chain. And so if we have mirror symmetry, that's alternating stereochemistry. So this one is whichever hand you want, left hand or right hand. Let's say that this is left hand, this is right hand, and you can't put these molecules on top of one another, so it's going to be different orientation in the chain. Whereas if you have something like this, if I take my left hand here, I can turn it around and I can make left-handed over here too, right? And so these are the same orientation. Same stereochemistry. So this is going to be isotactic. This one's going to be syndiotactic. So the important part of this is that you can design these metallocene catalysts. So Ziegler-Natta can't do this, right? Because Ziegler-Natta has no control over how the orientation of the molecules come in. So Ziegler-Natta catalysis can be used for isotactic polypropylene just based on the conditions of getting exactly the right temperature, getting exactly the right catalyst. And so Ziegler-Natta was the first way that isotactic polypropylene was made. But syndiotactic polypropylene and being able to tune the stereochemistry of, say, polystyrene, isotactic and syndiotactic polystyrene is really facilitated by these metallocene catalysts. And here we get much more regular arrangement of monomers versus Ziegler-Natta. We just have to get the conditions just right. So the percent tacticity is not as high. Is that okay, Kathleen? Okay.
Is it safe to say for the impurities of the emulsion polymerization are mostly from the surfactant?
That's right. So in an emulsion polymerization, what do you have? Monomer, initiator, surfactant, and what else do you have in emulsion polymerization? Water, right? Or some non-solvent for the monomer. So an emulsion is like oil and water, right? Monomers tend to be oil-like or hydrocarbon-like, and so you have monomer droplets that are stabilized with surfactant. So you have monomer, you have surfactant, you've got water, and you have initiator in the water, and so the initiator diffuses in to the monomer droplet and makes a polymer in there, and the polymer now is stabilized by surfactant in water. And what do we call this arrangement where we have polymer, surfactant, and water? What's that called? Buy it in the hardware store. A latex, right? So when we buy latex paint, it's got surfactant that's stabilizing this particle of polymer inside some water-based emulsion. And so this allows paint to be spread on very easily, right? Because the polymer's in these little droplets, we just have water as a solvent, so we can paint this on the wall. The viscosity is low because all of these little droplets aren't entangled. So we can make a nice coating out of this latex, just just like latex paint. Whereas if we had solution polymerization or something else, we'd have all these chains in a bulk polymer, and it's very hard, very high viscosity to spread out.
So emulsion wouldn't necessarily give you a pure polymer?
That's right.
Question on the homework.
So what's the problem with emulsion polymerizations? You have lots of surfactant in there that you have to deal with. So you either need to purify it later, or the surfactant just goes into the paint. So in this paint, there's surfactant in there. There's also color and all other stuff. Whereas if we make a bulk polymerization or solution polymerization, we can get very, very pure polymer
So
that way.
bulk and solution are the same?
So what's the difference between bulk and solution?
Bulk doesn't have solvent.
Bulk has no solvent, right? Just monomer and initiator. Solution has solvent to control heat transfer, to dilute the polymer, to keep the viscosity lower. And so you still have to remove the solvent from a solution polymerization.
But we can still count that as pure?
Mostly pure, because it's easy to remove the solvent in general. Easier than taking out a surfactant. Oh, Kathleen first, and then you, David. Go ahead, Kathleen.
I was looking at the homework solution for number 2.
Uh-huh.
On 6.6, it has 8 carbons between the two.
Bulk.
That's not right?
That's wrong. So which problem is this?
I think it's 1 on homework 2.
Let me go and fix that. So this is homework number 2. Problem number 1. It's for a diptic acid, right?
Yeah.
1, 2, 3, 4. So this is a diptic acid, so this is carbon 1, 2, 3, 4, 5, 6. So this is correct. My mistake. Not 6 carbons in between the acid groups.
And then PMMA didn't have a methyl.
Oh, it doesn't have, what did it have at the end? Nothing?
No, it just had an H, yeah.
Oh, whoops. Yeah, so PMMA, PMMA must have been me doing the structures late at night. So PMMA is this. So polymethyl methacrylate. That's right. Sorry, new homework, new solutions. There's some mistakes.
6?
Yes?
Do you have to memorize all the structures shown in homework number 2?
So remember, any structure that's been in the notes or on the homework is fair game.
Also like PMMA, we know, you need to know how to draw all.
Oh yeah, you should know. This is polymer class.
Okay.
Now, I'm not going to ask you for 20 structures on the exam. You don't need to memorize them all, but PMMA is probably important. Polycarbonate, nylon 6,6. You know, I've asked you some multiple times, right? And so the ones that I've asked you a lot of, you want to have like 3 or 4 common. Is this step growth or chain growth?
Chain growth.
Chain growth. So you want to have 3 or 4 common chain growth polymers in your back pocket, right, to remember what they are. Is this step growth or chain growth polymerization? Step growth. You want to have a couple of step growths in there. So just make sure you know something about the chemistry. I'm not going to ask you hundreds of different chemistry questions, but since this is a polymer class, if I ask you, give me 2 examples of a chain growth monomer, hopefully you know what styrene and vinyl chloride is or something like that. So have a couple in your back pocket.
Will you ask for mechanisms? Some like showing arrow pushing? Show arrow pushing?
I might ask you on free radical. I asked you a homework question on where does the radical form, right? So I think that's fair game. I'm not going to ask you like show me an SN2 mechanism or something like that. So anything that's reminiscent of questions that I've asked you on the homework, or things that we've done in class. I mean, that's what the test is going to be on. The test isn't going to be on different material.
How many questions are the exam?
I don't know. It'll be doable within 50 minutes, no, or 58 minutes. But I guess the formal exam period is 50 minutes, right? So, you know, if you think about, I don't know, how long does it take you if I say, please write down the structure of polystyrene and polyvinyl chloride? How long does that take you? 3 minutes, right? Or 2 minutes? So you can guess how long that's going to take. The exam's not going to be long, it's just going to ask you questions to make sure that you know something about polymers. So the exam is not to trick you, the exam is not to give you a C, the exam is to make sure that you're paying attention in class and make sure that you're learning some material about polymers. So this is an introductory class, right? Lots of you have never had a polymer class before, so I'm going to ask you questions that just relate to the basics of polymers. David, did you have a question?
Oh, I have a question.
Sure.
Like, I know, like, birefringence is the backbone minus the side bond, right?
That's right.
But I don't know why is backbone the perpendicular one and the side bond is the...
Okay. So, birefringence of a polymer is defined as the birefringence of the backbone minus the birefringence of the side chain. That's just our frame of reference. And so if we take a polymer and we stretch it out, let's say it's just a carbon-carbon bonded backbone, right? And let's make it polystyrene. This is the backbone direction. This is the side chain direction. So the backbone is the long part of the chain, right? So if we stretch out a polymer chain, it's going to look like this. So the backbone direction is this direction, the side chain direction is perpendicular to the backbone. So that's just by convention.
So side chain, so aromatic ring's gonna have higher refractive index.
That's right. So the refractive index in this direction is higher than the refractive index in this direction, and so polystyrene has negative birefringence. More polarizable, that's right. Refractive index relates to the polarizability.
So what kind of polymer doesn't have intrinsic birefringence?
Intrinsic negative birefringence? Or no, a birefringence of 0?
0.
Yeah. So if you make a copolymer, what's a polymer with a positive birefringence? From the notes. Polyvinyl chloride has positive birefringence, right? So this is a polar bond. It's not very polarizable. And so if we make a copolymer of vinyl chloride and styrene, one's got delta N is greater than 0. This one has delta N is less than 0. And so if you make a copolymer of these two in just the right ratio, you can get a polymer with 0 intrinsic birefringence. So you have to do something to the chemistry to make the refractive index of the side chain the same as the refractive index of the backbone. So you can blend polymers, you can make a copolymer, you can put other stuff in the polymer. But any monomer that's got intrinsic birefringence will give an intrinsically birefringent polymer if you have orientation. Is that good enough? Yeah. What other polymer has positive birefringence that you know about? This is polyvinyl chloride. What's that, Lay? Polypropylene. Now, polypropylene is going to be a toss-up, right? Because it has carbon-carbon bonds in the backbone and carbon-carbon bonds in the side chain. But PVDF has positive birefringence because it's not very polarizable in the side chain direction, and it's highly polarizable in the backbone direction. So this is delta N is greater than 0. And so you notice that this carbon-halogen bond, this carbon-halogen bond, and so that tips you off because the electronegativity is much different between carbon and chlorine and carbon and fluorine here versus carbon-carbon. And so these halogenated polymers tend to have birefringence that are greater than 0 because they have polar bonds in the side chain.
What about HDPE?
High density polyethylene. Which one's more polarizable? Carbon-carbon or carbon-hydrogen? Carbon-carbon bonds are more polarizable, right? Because it's the same electronegativity, and so you can shake those electrons around because neither carbon prefers to have the electrons, whereas carbon-hydrogen bonds are polar, right? There's different electronegativity between carbon and hydrogen, and so HDPE is going to have birefringence greater than 0. More polarizable along the backbone, less polarizable along the side chain. Yes?
Are there any functional groups or side chains that are going to be like especially polarizable, like the phenyl group?
Yeah, so phenyl is, methacrylates are because they have that ester group. You know, things with lots of electrons are polarizable, right? And so if you make big side chains with lots of electrons, they'll be highly polarizable.
So if we have alcohol attached to the carbon backbone, is it going to be more polarizing?
Like this?
Yeah.
Polyvinyl alcohol. I'd have to see, oxygen is pretty close, so this is going to be close, right? Because we still have carbon-carbon bonds here, but we do have, what's special about oxygen? It's got some lone pairs on it. And so we would have to look up the polarizability in this direction versus the polarizability in this direction. Some are going to be too close to call, and so we would need some more information, or we'd have to go to the book to look at the polarizability of carbon-carbon bonds versus the polarizability. That's known, but some structures it's hard to know by just looking at them. If you know the major examples, that's the important part.
Do we need more cross-coupling polymerization for Suzuki?
So I think the only thing you need to know about cross-coupling polymerizations is it involves what type of catalyst. Cross-coupling, you need what? A metal, right? And so that metal is really important for cross-coupling polymerizations, and so that's probably all you need to know about Suzuki. And they won a Nobel Prize for Suzuki cross-coupling, so it's probably important to know that. Although this won't be a test on Nobel Prize winners, so that's fine. But yeah, I mean, Caroline, since she gave the lecture on metal facilitated polymerizations, just knowing that Suzuki is one of them is important. Yes?
Can you explain about DSC graph?
Sure. Okay, so what do you want to know?
Like, why is there peak whenever?
Ah, okay. So what does DSC measure?
The heat
flow.
Heat flow, right? DSC measures heat flow. And so heat flow in watts, and this is going to be temperature. So we're going to measure thermal transitions in DSC. What's the lowest temperature thermal transition in polymers? TG, right? And so a TG, so let's do endo up. An endothermic process does what? Takes in heat. And so TG, you have this baseline shift. And so it turns out that TG going from glass to liquid, you have to add heat, so it's an endothermic process, right? And so anytime you see a peak, so this is an endothermic What other endothermic process do we have that occurs above the glass transition temperature? You add heat to do what? To melt, right? And so this will be a Tm, or a melting temperature. And so we can measure the delta HF of this polymer by how it melts. And so the way this experiment would be run is that you crystallize a polymer between Tm0 and Tg, right? You cool it down below its glass transition temperature, and then you warm it back up, so this is a heating scan. First you go through the glass transition temperature, which is a second order phase change, and so you have this shift in the baseline. It's just good to know that. And then you have a first order endothermic process, which is the melting temperature, and that's where you get the heat of fusion from.
What if we see the bottom side peak?
So the other way that the DSC can be run is, let's do heat flow. So the other way DSC can be run is it can be run from the melt. And so if we do a cooling scan, what we'll see is we'll see a TC. We'll see crystallization peak as we cool. So we'll see a TC, and then we'll see some sort of TG as well. So first, we might call this the first cooling scan from the melt, where we get crystallization. Now if we heat this thing back up, what's going to happen? So if we do a first heat, what might happen? You're going to go through TG again, right? And so then we're going to melt those crystals. And we know that Tm is always greater than Tc. And so we form the crystals at a certain crystallization temperature, cool down to Tg. Then we heat this thing back up, we go through the Tg again, and then we're going to melt those crystals at a higher temperature than Tc. And so with DSC you can track the formation of crystals, and you can track the melting of crystals, and of course you can measure glass transition temperature. So it just depends on what state your sample is in. If your sample already has crystals in it, you can measure the melting of those crystals. If you want to form crystals in your sample, you can measure that formation. And so oftentimes you see DSC is shown like a loop, where there will be some sort of melting first, and then you come back and then you see the crystallization, and those peaks will be offset by a little bit. Is that cool, David? Yep. So just make sure that you know that melting is an endothermic process. Crystallization then is going to be an exothermic process. Does that make sense? Yeah? Good. And so again, I'm going to test you on the basic stuff. So I want to know that you're learning stuff from the notes. I want to know that you're paying attention to stuff from the homework and in class. And so that's going to be what the origin of the questions are. So there will be some things that you just write down. There will be some things to figure out. There will be some what-if questions. And so I'll ask you questions like I asked in the homework. And there will be plenty of partial credit, just like there is on the homework as well. Yes?
Can you bring a calculator?
Yes, bring a calculator. The math will be easy if there's any math on the thing, so you can do it by hand if you want. So you're not going to need a calculator to pass the exam, but you can't use your phone. That's, or your tablet or computer, whatever. Is everyone good? Okay, I'll see you tomorrow. Remember, the exam is in class, so.